So we have calculated the derived the expression for the partition function of a two-dimensional classical ideal gas, and that expression which we found out was 1 by n factorial v raised to 2 by 3 by h squared 2 pi m kt raised to n. So that was the expression which we calculated. So I just wanted to tell you one more thing. So there is always a question of single particle partition function. So there are books which try to calculate the single particle partition function and then extend it to n particles. So there should not be any ambiguity in the case of classical ideal gas in that case, because then it works based on the expression Qn Vt is equal to Q1 raised to n. Since this is an ideal gas, you have to divide it by n factorial. So therefore, here the single particle partition function will turn out to be Q1 is equal to v raised to 2 by 3 by square 2 pi m kt. V raised to 2 by 3 by h squared 2 pi m kt. So if we need to know the single particle partition function, and there are certain problems here and there which need to start with the single particle partition function. So there you can utilize your knowledge which we derived. Okay, so now we will continue with we will try to basically help you with the derivation of some of the thermodynamic parameters. So I think you should get used to deriving the partition function for any given system, and then evaluating its necessary thermodynamic parameters. So here we will take the A is equal to Helmholtz free energy. So Helmholtz free energy A is equal to minus kT ln Qn, right? So I can of course substitute the Qn value over there is equal to minus kT ln 1 by n factorial v raised to 2 by 3 divided by h cube into 2 pi m kt raised to n. Okay, so that is it. I just simply applied that here and that over there. Now one thing which I can do, the most simplest thing is to apply the Stirling's approximation, and then I can write as A is equal to minus kT ln v raised to 2 by 3 divided by h squared 2 pi m kt raised to n minus n ln n minus n, right? Right. So therefore I can simplify that as minus n kt ln v raised to 2 by 3 divided by n h squared 2 pi m kt plus 1. So you can cross check it yourself. I have done this quite long time back. So these are, I might be jumping the steps over there. So I just want to give a guideline for you so that you reach some expression. That's all my intention is. So one can do it, one has to do it themselves for your satisfactions. nkt ln n squared by v raised to 2 by 3 1 by 2 pi m kt, right? Because we have removed the minus sign from the ln. So that's all. Minus 1. So we stop there. So this is one of the expressions possible for the a. See, there is a room for improvement for all these quantities, always. Depending on the next step of the derivation, one can always manage these equations according to your mathematical convenience. So there's no statistical mechanics really involved in there. It's purely about our mathematical conveniences, right? So S is equal to minus dou A by dou T. So I can apply that, the A, I will apply that over there. So, and then I can, write it as, and jumping the steps, which I myself have written here. Nk ln nh squared divided by v raised to 2 by 3 1 by 2 pi mkt minus 1. Right? Which I can write it as nk ln v raised to 2 by 3 divided by nh squared 2 pi mkt plus 2. So that's it. So this is one of the final expressions possible for the entropy of the system. And correspondingly, if I need to calculate the pressure, so pressure is equal to pressure when it is connected to the Helmholtz free energy. So that expression is P is equal to minus dou A by dou V, right? I have listed those set of expressions in one of the previous videos. So that will come out to be, if you can try it yourself. So P is equal to 2 by 3 nkt by V. So this is the expression which you should be getting. And mu is equal to dou A by dou N. And which I got it as kt ln nh squared by v raised to 2 by 3 1 by 2 pi mkt. U is equal to A plus Ts. What is U? U is the average energy of my system. U is equal to A plus Ts. I can apply the expression for the A and the S. I have the expression, we have found out the expression for the A and the S, right? So I substitute that over here and I write it as nkt ln nh squared by p raised to 2 by 3 1 by 2 pi mkt minus 1 plus Ts, right? So nkt and then v raised to 2 by 3 divided by n squared 2 pi n kt plus 2. Sorry, I should be doing this. Right? So, you do the mathematical adjustments over there, where you take the nkt inside and do the adjustments there. Then finally, what I get is that minus nkt plus 2 nkt from here. All the other terms will get cancelled out. So minus nkt plus 2 nkt is equal to nkt. So this is the expression for my u, which means that now I am in a position to calculate the value of what? Cv and Cp, right? So Cv is equal to dou u by dou t. So this will come to be nk, right? Because u is equal to nkt. And Cp is equal to dou h by dou t. And h is equal to u plus pv. And p I have already found out over here. P is equal to 2 by 3 nkt by v. So therefore pv is equal to 2 by 3 nkt. So h is equal to u plus pv. So therefore nk plus 2 by 3 nkt. So which will come to be 5 by 3 nkt, right? So dou by dou t of 5 by 3 nkt. So which will give me Cp to be 5 by 3 nk. Right? So I have jumped the steps in a couple of them, like in the case of A and S. Try to solve it yourself and gain expertise in solving such kind of mathematical expressions. Okay, so that's it for the two-dimensional classical ideal gas.